Okay, let's get started. So, I will just finish a couple of slides from last time, then we will have a new topic which is on naming. Also, just as an announcement, I have gone and adjusted the class schedule because we did not actually have our makeup class last Friday due to other scheduling conflicts with candidates Friday and so on. So, I had to make a few changes to which order the lectures are going to be in. So, if you signed up to be a scribe, you need to make sure you know which date the lecture that you signed up for is actually going to happen. That is the main implication of what I changed. Nothing much else has changed. We will still be able to cover all the topics. We will just have the cancelled makeup class at a later time. Okay. The other announcement which I already said on Piazza is there is no class on Friday because I am going to be away. Okay. All right. So, last time we were talking about video and audio streaming, and I mentioned how video streaming works. We talked about this notion of quality of service and so on. Okay. There is one last thing I want to talk about there, which is stream synchronization, and then we will start a new topic which is going to be on naming. Do you have a question? Yes.
So we have no class on Friday. We also have no class on Wednesday?
Sorry, I meant no class on Wednesday. Did I say Friday? There was never a class on Friday. So, yes, that is my mistake. Thank you for pointing that out. So, no class on Wednesday. We resume classes after spring break. That is what I meant to know. All right. Okay. So, so the last thing I want to mention about streaming is this notion of stream synchronization. Okay. And so, this is going to arise in multiple contexts where you have, let us say, a microphone and a camera that is capturing a live image. Let us say you are doing a video conference over Skype with someone. Okay. So, your device that is being used for Skype is going to have a camera and is going to have a microphone, is going to capture two streams, an audio stream and a video stream, and is going to send that over to the other end. And when it gets played out, the two streams have to be synchronized. Okay. And the reason is you want, when the video is played out, the audio that is being played out at the same time has to be lip synced. Otherwise, you see someone saying something, you see their lips move, but what you are hearing is not what they are saying. So, this brings up the need for stream synchronization, which is basically what this slide is showing. And there is a picture, I believe, in the next slide. That is not that useful a picture. But the point that I want to make is stream synchronization can be done in many different ways. Okay. Timestamping is the simplest way. Okay. If you are capturing two streams on a device, that device will have a common clock, then you just use that clock to timestamp. And when you play it out at the other end, you look at the captured timestamps and you want to make sure that the audio and video that you are playing out have the same captured timestamp. So, then you can play out the audio and video at the same in a synchronized fashion. Okay. Now, if the audio and video are captured by multiple devices, you are going to have a problem unless the clocks on those devices are not synchronized. Okay. There are two machines, one to do audio capture, one to do video capture, and then you play it, you mix those streams, send it over and you play it out. Then you want to make sure the clocks of those devices are going to be synchronized. Otherwise, if you just use clocks without synchronization, you will be out of sync. Okay. Very soon, which is next class, we are going to talk about how to do clock synchronization. So, here to stream synchronization, you either need synchronized clock across all machines that capture a stream. Okay. Or if you are using the same machine or the same phone or the same laptop is capturing an audio and video, then there is no problem. There is only one clock on that machine that is used for timestamping. But timestamping is essential part of synchronization, and what this is actually showing is essentially you see that there is a speaker and there is a screen, and the video is being shown on the screen. The speaker is playing out the audio, and the decoder here is actually looking at two streams, an audio stream and a video stream that is coming over the network, and then it is decoding them using the timestamp to sync them and play them out at the same time. Okay. So, that is the basic point that is being made there. And with that, I am going to stop with our discussion of synchronization and move on to the next topic, which is on naming. Okay. So, this is going to be the shortest chapter or the shortest topic of the entire course. We will not even spend the whole lecture on this. But be that as it may, it's an important topic for you to keep in mind. So first I'll describe what is this problem of naming, but then the most of the class is going to be focused on how do you do naming or solve this problem in large scale distributed systems. That's what we want to understand. Okay, so what is naming? So essentially naming is a mechanism that allows you to map a name of an object to some value of the object. Okay. When you did your lab assignment, if you used RPCs or RMIs, you used a naming service. Okay. So you have already used naming. In that case, naming essentially allows you to map the server to its IP address and the port number, the server that is actually going to expose your RPC call. Okay, naming can be used in many different contexts. Name servers are used widely for a variety of different scenarios. The one that we are going to talk about today is actually the domain name service as an example of a large scale naming service. Okay. In domain name service, you are actually given a name of a machine, you translate it to the IP address of the machine. Okay. And we will see other naming systems that do other things as well. All right. So that's basically the goal for today, and as part of that, we'll also try to understand when you type something like www.somewebsite.com into your browser, how does that get resolved to an IP address? Okay, because your browser actually needs the numeric IP address of the machine corresponding to that URL or that name in order for you to make a connection, HTTP connection to that machine. So that's just going to give us an example of how naming is going to work. Okay. So we'll talk about three things today, actually maybe two. The first one is just the concept of naming in a little more detail. Then we'll look at DNS, and then we'll look at other naming systems. Okay. So whatever your naming system that you are using is, we'll use one of two types. Okay. One could be P2P name resolution, the other is hierarchical name resolution. Okay. So in the first case, we already encountered this. When we have a P2P system, you can specify a key, and that basically gives you a value. So essentially, this is the CORD P2P system that is being shown here. It was a distributed hash table that allowed you to do a lookup. Okay. So you can think of writing your naming system on top of a P2P system of this sort, where the key is the name, and the value is whatever the name needs to resolve to. Okay. And then you have a peer-to-peer naming system. Okay. You can also take your naming system and make it hierarchical in nature, which is shown on the right here. In this case, your essential naming system is basically going to be broken down into hierarchies, and then we will see that's the one that we are actually going to look at for the rest of the class, not the P2P one. And we are going to see what these hierarchies mean, why do they need to exist, and so on and so forth. Okay. The important thing you want to keep in mind is when you have a very large scale distributed system, your naming system itself has to be distributed. Okay. Because there are lots of names and there are lots of requests, so you can't actually run the entire name service on one machine. This is an important difference from whatever you may have encountered in your lab, where you might have started a name service and you registered with that naming service. That was a centralized single machine naming service. But if your naming service is to scale to very large numbers of users, it can no longer run on one machine. It itself has to be distributed. Okay. The applications and users are distributed, the naming service itself is distributed. And so that is why we are actually looking at these two examples. Obviously, a P2P system of this sort is distributed inherently. There are many peers participating in name resolution, and so is a hierarchical system. Okay. You had a question, yes?
Traditionally, for a ring topology, does the traffic only go one way or both ways?
Okay. The question is, traditionally for ring topology, does the traffic have to go one way or the other way? So the problem of how the traffic flows through a topology is called query routing. Okay. You make a request, how does that query route through the network? There are many routing schemes that P2P systems might use. So for example, if you just say everything goes clockwise, that may not be so optimal if the node you want is actually one hop away in the other direction. So typically, you might have some intelligence that says which of the two paths is shorter and send the query along the shorter path. Right. So there are that, but that's a query routing protocol that layered on top of this. Okay, you can have different query routing protocol. So long as you get the answer, that's what you care about. But they do try to optimize the resources, use the hops that you need to get the answer, and so on.
Cool, thank you.
Okay. Any other questions here? Okay. So, let us start with something that you may have actually encountered already, which is file names, and see how name resolution works in case of file name. Okay. So, first of all, you need to understand that when you are using a file system on your machine, okay, your OS actually is performing name resolution. Okay. Because internally, as far as the OS is concerned, okay, files are actually numbered, they are given numeric IDs. Okay. Humans also give you textual names to files, so that you can remember this name for your purposes, because it is harder to remember numbers, but you can actually organize your files into folders and give them names and so on. Okay. So, now when you actually open an application and try to access a file, what has to happen first is your OS has to take that name of the file and actually map it to the actual internal ID of that file, which is the number that it has associated with the file, and then the OS is going to work with that ID of the file. Okay. So, this process is going to be called name resolution. A name resolution is going to involve multiple lookups if you are actually using a directory structure. So, what is shown in here, okay, is a simple picture that shows the directory structure of a machine, where you might have a root directory. The root directory has two subdirectories called home and keys, and then in the home directory there are user directories, which are Steen and Max and so on. So, these are actually users on that machine, and within their home directories they might actually have files or other directories that they have created. That is your directory structure that you might have on any machine, typical machine. Okay. When you try to open a file, in this case we are trying to open file /home/steen/mailbox, which is the mailbox for inbox for that user. Okay. If you try to open this file, the way the file system is going to track down this file is through a hierarchical name lookup. Okay. It is going to start with the root directory, okay, and basically look at the index node or the inode on that root directory, which is the metadata for that directory, and say, is there a subdirectory called home in it. Okay. Once you find that subdirectory, okay, then you are going to go to the next part of the path. You open that directory called home, and then you ask, is the next part of that name actually present in that directory. So, you are going to ask open home and say, is there a subdirectory called Steen in that directory home. Okay. If that lookup succeeds, then you actually go to the directory Steen and say, is there a file, in this case file called mbox present in that directory. So, you are going to recursively traverse this tree, okay, based on that name and try to locate that file. And once you hit that file, you are going to open the metadata, which is the inode for that file, and say what is the ID of that file. Then you get the numeric ID. Okay, so, you have done a recursive lookup. This is how a file system would open any file that you open when you use an application. Okay. We are going to use that same concept to do name resolution in other system. Okay. This is just an example for you to understand that some of these things are actually common across naming system, including file systems. But before we go and look at naming systems more broadly, I just want to give you a simple example of how name resolution might work when you have a distributed file system. What I showed you on the previous slide was a file system that's entirely present on a single machine like a laptop. Okay. But in a distributed file system, you might have file clients, okay, and servers. Okay, your two machines, your A and B. Okay, the files on the server are actually accessible to the client through a network mechanism, such as a network drive or NFS or a network mount of some sort. Okay. Then you should ask, how is name resolution going to work in this case? Okay, so, in this case also you are going to look at that same file /home Steen mbox, except that that file is actually present on a different machine from the one that is trying to look up that file. Okay, the lookup, you are trying to open that file on the client machine, the file is actually sitting on the server machine. Okay, but you still have to do name resolution to track down that file. So, what you will do is you will basically traverse down the root hierarchy the same way you did, but when you hit the mount point, in this case you are using NFS. So, you mounted that volume here on this machine. When you hit the mount point, you say this resolution has to actually happen on the server, because it is a remote file, not a local file. Okay. So, then you simply send that name resolution request after the server and saying go track down this file. Okay. So, multiple machines are participating in name resolution here. Part of the lookup is actually happening locally. Once you figure out the file is remote, you then send that request off to the other machine to resolve it. Okay. Very simple concept, but when we talk about distributed naming, we are going to do the same thing. you are going to use multiple machines to get the answer. Each machine is going to do part of the name resolution for you. This is called name resolution. Any questions here? Okay. All right. So, now I am going to talk about DNS specifically as a use case of a large naming system. Okay, so, first let us try to understand, for those of you who are not that familiar, what is DNS. DNS stands for domain name system. Okay, it is basically the service in the internet that allows you to specify any machine name and get an IP address for that machine name if it is valid. Okay. Practically any networked application that you use, whether it's web browser or SSH or FTP clients or any of these, are going to first use the domain name system to get the IP address and use the IP address to make connections to those machines. Okay. So, given that this is the naming system for the internet, okay, the naming system has to also scale to the number of users and devices you have in the internet, which is billions of devices. Okay. So, you can't put that entire naming system on one machine and expect it to service the workload of all name resolution requests that are coming. So, it has to be distributed across multiple machines. Okay. And the way they have done this distribution is through a hierarchical framework, which I will show you on the next slide. Okay. So, essentially you have the notion of domains. Within domains there are subdomains and subdomains and so on. So, any name that you see such as www.cnn.com, okay, is basically is recursive in nature, where you have first the top domain is .com. Okay. Within .com you have an organizational domain, which is CNN. Within that organizational domain you might have additional subdomains and so on. So, you are going to have an hierarchical framework that you use in your naming system, which is actually shown in this picture. It's better to use this one. So, you will see at the top you have what are called top level domains. Okay. This is a very old picture. Now, there are hundreds or thousands of top level domains, but at one point you had .com for all companies and .edu for all educational institution and this .gov and so on, and every country also had its own top level domain, which was a dot followed by 2 letters for represent that country, and within that you could have other subdomains. Okay. So, those are all top level domains for the internet. Now, there are lots and lots of them. Okay. There are hundreds of top level domains, but these are still the more popular ones, okay, that you will encounter. Now, if you are a certain kind of entity that belongs to that category, if you want to actually have your own domain name, you have to register one, and then you basically get your own domain. Okay. So, you have sun.com or you can have umass.edu. So, those are actually domains within different top level domains, and then once you have a domain, you have organizational access to create additional subdomains. Okay. So, you might have cs.umass.edu. CS is a subdomain within umass.edu. Okay. And you can have further partitioning. You can say www.cs.umass.edu. That is yet another level of organization. Okay. At the bottom of this are going to be machines, okay, and then subdomains, domains, group machines in some hierarchical organizational structure. Okay. Now, that may be all obvious in case of DNS, but the same principle applies to many other kinds of distributed name services, where you have a hierarchical naming scheme. Okay. The organization here is actually what is called a naming scheme. This is how you come up with names for machines. It is hierarchical in nature. Okay. So, the naming scheme is hierarchical. Okay. Name resolution, as we will see, also uses this hierarchical framework. Okay. So, those are the principles we are going to extract from our study of DNS. That is going to apply more broadly. Okay. Yes, there is a question in the back. Okay. The question is, if I understood what you said is, I said that the naming service is distributed, but here you actually see one node at the top. Okay. What this is actually showing is the name space. This is not the servers in the naming in DNS. Okay. Namespace is how the names are organized. Okay. So, that is basically going to be the root node and then the top level domains. That does not necessarily mean the servers have to be organized this way, but in many cases the namespace also gives us a hierarchical organization of the name servers. Okay. But having said that, there's still not going to be one name server for all of the internet representing that. That's not going to scale. Okay. We actually have top level name servers for the domains, but not for the root. Okay, that's something you want to keep in mind. But yeah, that's a good point. You have to distinguish between the namespace, which is how names are constructed, and the name service, which is how those names map onto naming services, who is responsible for what. Okay. So in this case, these 3 layers are actually given separate names. So at the top level is called the global layer of the namespace. This is called the administrational layer. That's called the managerial layer. Okay. This is the names don't matter as much as what actually we are trying to do. Okay. So these are essentially organizations. These are machines within that organization and so on. But the more important point is, as you go down the naming hierarchy, there are more frequent changes to the naming system. There are more updates happening. Machines come, machines go more frequently than organizations come and go. Okay. Top level domains almost never go, they only come. Okay. You add more, but typically you don't delete any. Right. So if you look at this hierarchy, there will be more changes that you will see, more dynamics at lower in the naming hierarchy than upper level. And that's important. We'll come back to that, why that is important when we do name resolution. Okay, but just keep that in mind for now. Okay. So now with that very quick introduction to DNS, let's look at a little more detail what DNS does. Okay, so first thing to keep in mind is DNS is a very simple lookup service. It's a key value lookup. You specify a key, you get a value. You specify essentially a name, you get a value. It does not do anything more sophisticated than that. Okay. You can't do any other kind of query. There's only one type of query, which is you have to give a full name of a machine and you're going to get the IP address of the machine. Okay. And the way it's going to do this is the servers that are part of the DNS are going to basically have several types of records. Think of them as they can maintain databases of records within the DNS. Okay. And there are many kinds of records you can store. Here are some common type of DNS records. Okay. The most common one is what is called an A record. Okay. That's basically going to take the host name and map it to an IP address. That's the simplest record that's the one that is also most commonly looked up, where you give a name and it gives you a value. So that record is an A record is going to give you those kinds of that kind of information. There's something called an MX record. Okay. MX record is used to specify the mail server for a domain. Okay. If you're trying to send email to somebody in a domain, typically you are going to actually go look up the MX record for that domain and connect to the specified mail server for that domain. This is how, if you get email for user@umass.edu, it's not the machine that has the IP address umass.edu that's receiving mail. You are going to say what is the mail server for umass.edu is going to be specified in an MX record, and then you connect to that mail server. Okay. And I'm going to show you some examples in just a moment. Okay. An NS record basically is the IP address of the name server or the DNS server for that domain. Okay. Typically, you might actually store the NS records of lower level domain servers, for example, so that you can do recursive lookups and so on. Okay. And here's another interesting record. It's called CNAME. That is an alias record. It allows you to give multiple names to the same machine. Okay. A machine no longer needs to actually have one name. You can construct aliases for it, and you'll see that there are many other tricks you can play as well. Okay. So here's okay. So now with that background, let's talk about 2 common ways to do name resolution. Name resolution is just a way of figuring out, I made a lookup request, how do I get the answer? Okay, I specified a key. How is DNS actually going to give me the answer? There are 2 ways to do this in general. One is called iterative, the other is called recursive. Okay, and they are very simple ideas, but here's how the iterative resolution is going to work. Okay, so here, let's say, is a browser that has tried to look up www.cnn.com or www.umass.edu. Okay, your local machine is going to run a name resolver, which is responsible for performing this lookup. Okay, so in this case, the example machine that you are going to look up is ftp.cs.vu.nl. Okay, so that's the example from the book. So what happens is, so that basically is a machine. NL is the country top level domain for Netherlands. So what you will do is you will first go to the DNS server for Netherlands, which is the root server for Netherlands as is shown on the right there, and say, is there an organization called VU in that top level domain? If so, what is its name server? What is its DNS server? Okay. So, you will basically do a lookup at that root name server and it will say, yes, I do have that. Okay. So, then you are going to, well, first you will go to the root and ask for Netherlands, but once you got Netherlands, you are going to ask for the domain name server for VU, that is a university in Netherlands, and then you go to the iteratively basically do the same thing. You go to the university name server and say, is there an organization or subdomain called CS, which is computer science department there. So, what is the DNS server for that? And then you go get that. And then once you get to the CS domain name server, you say, do you have a machine called FTP? Okay, if so, what is its IP address? Okay, and you will get back at this point the IP address of that machine. Okay, so, you are iteratively going through the hierarchy. You are just basically doing recursive descent, exactly what the OS did when you tried to look up a file. You started from the root and then you did a recursive descent to the tree. You are going to do the same thing here. You are descending down the namespace until you hit that machine and you get its IP address. Okay. This is iterative. Okay. Here is another way to do the same thing. It is called recursive name resolution. Okay. Same idea, okay, same example, but you are going to recursively do this rather than iteratively. So, you just inject the request to the name server saying, I want to resolve this name, you go figure it out, get me the answer. Okay. So, the name servers are going to themselves propagate the request down the hierarchy, as opposed to returning answers one at a time and then the client machine talking to the next level name server. You just inject the request at the top in step 1 and it basically keeps trickling down the hierarchy until you hit the lowest level name server. You get the IP address, the answer trickles back up to the root name server, you get back a response. Okay. This is called recursive name resolution as opposed to iterative. Hey, your question, yes.
Is there a benefit of using one over the other?
Okay, a good question. Is there a benefit of doing one or the other? That was going to be my question. So, let me ask that question and say, so what are the pros and cons? Why would you use one or the other? Yes.
So for the iterative name resolution, you can think of like maybe you have a query for a name that it has to go through if the name server is in Netherlands, you have to go to the contact.
Yes.
Here again, contact. So there are a lot of round trips and also time also involved.
Yes.
So but for the recursive one, there isn't this problem.
Right. Okay. Yes, good point. And I will explain that what you just said in a little more detail. You had something else to say? Same thing? Okay. So, the first thing is you can ask what are the performance implications of doing one or the other. Okay, and there are multiple things to keep in mind. One thing that was mentioned is if the name that you are trying to look up is in a region, geographic region that is far from you. If you are doing iterative name resolution, because a client is local and all those name servers are going to be also far from you, each of these requests is going to take a long round trip time. In this case, if you are in the US and that name, all of those machines are in Europe, there is going to be essentially a transcontinental hop that you have to incur for every request. Okay. In the recursive one, you basically just send one request that's transcontinental and then the reply is just going to trickle down from one machine to another, but that's within the same geographic area. So, that latency is lower and then you get one reply which is a transcontinental. So, there are multiple long RTTs in iterative, there are fewer long RTTs in recursive if the distance, the geographic distance between the client and the name you are trying to resolve, that region is far. Okay. If they are close to one another, then this may be less of an issue. But there are often names that you will resolve that are in a different continent. Okay. That is one problem or one issue with iterative name resolution. Any other thoughts? Yes.
So one thing I did notice is that in the recursive methods, each server has to make connections to the lower level of the hierarchy. So I'm guessing that means the number of active connections on each server is higher. So even though the clients are doing less work, the servers are probably going to be doing more work in this method.
Yes. Okay, so the second issue we want to keep in mind when you talk about name resolution is what is the performance impact on the servers. The first one was performance impact on the client where the RTTs were long. So here if you think about it, in recursive name resolution, every request for a domain is going to start with the root. Okay. All requests are going to go through the root. So the root is going to see a very heavy load. Okay. And the next tier is also going to see a pretty heavy load as well, because that country name server will have to basically be in the path for all requests that are actually resolving to any machine within that country. So higher up in this hierarchy, the loads on those root name servers is going to be very, very high. Okay. Now, you might say, why is that not true in iterative? Aren't you actually also connecting to the root name server and so on? Okay. That is indeed true, but the thing that you can use to your benefit is caching. Okay. You can actually take the responses that you have received previously and cache them. Okay. So for example, now after connecting to those name servers and getting ftp.cs and the whole thing, if you want to now connect to the web server of that machine, www something, if you have cached all the responses, you don't have to start at the top. You say, I already know the name server for that university or in the computer science department. Instead of looking FTP, I want the web server for that machine. You can directly connect to that name server and get the reply. Okay. So caching is going to reduce the load on the higher level name servers in iterative name resolution. Okay. And this is where the issue I mentioned, which is there is more activity at the bottom of the hierarchy than at the top, helps you. So you are going to be able to cache the top level replies for long periods of time because they don't change. Okay. So the cache timeouts or expiration times on those cached values can be long. Okay, but lower down the hierarchy, you might have to give shorter timeouts because maybe those things change more, well, not that frequently, but you are not going to keep them for long periods of time. So essentially, the higher up the hierarchy, you want to cache as long as possible because that reduces the load on those servers quite significantly. Even if you have to come back 1 week later and look up for something in that country, if you have already done some part of that name resolution, you can carry from that point on. Okay. So if you now want to look up a different university in that country, you just start at NL, you don't start at the root. If you want to just look up different department within that university, you start at the university name server, don't start at the top. So you can cache previous responses and reduce that overhead. Okay. In case of recursive, you are always going to send the request to at the top, so you don't have any benefit of caching as far as load is concerned. There may be internal caching to send replies, but still the root is going to see all of that load. Okay, so you have these two performance trade-offs, which is actually shown in a picture here, which is exactly the discussion we had, where if you are doing recursive, you are going to have load on those servers. If you are going to do iterative, there is going to be a lot of round trip time because the distance between the two is high. And caching is going to help you in case of iterative name server. So most of this name resolution for that reason, for scalability reason, tends to be iterative. Okay, because otherwise you are not going to scale if every time you are doing any name lookup in the internet, if you start at the root name server, that's just not going to scale. Okay, yes, question.
I was wondering how the client knows where to look up for the root server.
Okay, how does the client know where to look up for the root server? So the DNS resolver, because you have to actually run a local name resolver. Typically, that name resolver is your local DNS server. Is configured to with the right things, that it knows what the root levels are and so on. Your machine actually is not doing this. This is a false equivalence, is not being done at the client. What you will do is you will actually send a request. There will be one DNS server somewhere in your LAN. Okay. You send it there, that does the resolution and gives it back. Even on your home Wi-Fi network, typically a router will actually take that as the local name resolution request. Okay, so your client doesn't do it, your router will actually do it for you. And it has, because that is running a DNS service, it knows what the root levels, those are coded into the service. Yes, you had a question.
Is it possible that you can cache in this case, where you go to the NL node instead of the
Okay. The question is it possible to cache? You can indeed cache previous responses. So if some other user wants exactly the same name, if you cached it all the way to the hierarchy, you don't have to send the request all the way down. What that is doing is alleviating load lower in the hierarchy, but that's not where the problem is. The problem is higher up in the hierarchy. So you're not reducing the load higher up. Okay, but yes, you can use caching. Yes.
You can also make a replica of the root name server, distributed everywhere in the infrastructure.
Yes. The question is, can you replicate? You can always replicate higher levels of the hierarchy or lower levels of the hierarchy. Replication is always a choice in any distributed systems, but you got to then maintain consistency. Anytime you replicate any data, because what you're replicating is the records, you want to make sure if there's a change, it's going to propagate and so on. And this is where there are problems, because DNS uses a very loose form of consistency. If you change any DNS entry anywhere, if you have actually done any of this, you will know that it will say it might take 24 hours for the results to be visible. And the reason is DNS servers exchange information once a day. So you make a change, it may take until tomorrow for that change to be active. Typically, it doesn't take that long, but the default is once a day. Many DNS servers have started doing more frequent exchange of updates, so you don't see that problem, but it may take up to a day. So that's another problem. There was a question here. You had a question? Okay. Okay. So that's name resolution, and then I just want to show you some example. So these are some actual records, and this is taken from the book. I mean, in a moment I'm going to show you how you can do your own lookups and get some of this information. So you will see, I don't want to go through this entire table, but I would like to point out that here is an A record, right? So the A record actually has this name and it maps to that IP address. Here is an MX record, that's basically the mail server for that domain. Here is essentially an alias. So it says www.cs for the web server. It's actually an alias for that machine. So if you want to connect to the web server, go and do a lookup on that machine instead. So then you do a second lookup, which goes here, and then you look up the A address, A record for it. Okay. So this allows you to give that name, that machine, a second name. In fact, you see that it has 3 names. It has the name web server, FTP server, and the actual name. Okay. So machines can have multiple names. You can register them through DNS. Okay. Yes, you have a question.
Sir, what are the 2 parameters of the MX record? The others all have just 1.
Okay, so that's a good question. What are the 2 parameters of MX records? So you'll see that there are 2 mail servers for that domain, and that is just saying that that's the first one you want to contact. If that is down, contact the next one. So you can set priority level, saying if to talk to the highest priority one, then go to the next one, and so on. Okay. There's one interesting thing I want to show you here, which is I said that a machine can have multiple names, and you do that through CNAME. You will see here that this name star.cs has actually 2 A records, and they map to 2 different IP addresses. Okay. So what does that mean? Why does the machine have 2 IP addresses? Yes. Yes. So so the reason you want to give one name to IP addresses is if you want to do what is called DNS level load balancing. Okay. Typically, it is done for web servers. So you can replicate the same web server on maybe n machines and register all of them. So you will say www.cs.umas.edu has 4 IP addresses. There will be 4 A records. Okay. When you do when your browser does DNS lookup, it's going to get all of them. Okay. And then it can pick one at random and connect to that one. This means that when multiple users are connected to them, because they randomly choose one of the replies, the load gets partitioned automatically at DNS. You don't need to actually have a load balancer that is doing explicit partitioning. Okay. Different machines, different browsers automatically connect to different machines. In fact, what the DNS will also do is it will actually return them in different orders. Rather than always returning this in 1 and 2, you will basically reply by scrambling them, because most browsers actually take the first entry and connect it to it. They don't actually say, I got 4 replies, let me randomly pick one. They always pick the one at the top. So the easiest thing is for the DNS resolver is to return them in different permutations, okay, so that the one on the top keeps changing. That automatically splits your load across multiple machines. Yeah. So this is basically a load balancing mechanism at the DNS level. Okay. And we will see there are extensions to this as well, but this is a very simple clustered web server where you can use multiple names, multiple IP addresses for the same name. Okay, you can also have multiple names for the same IP address that you do to CNAME. Yes, question.
Are there any security concerns with me possibly using my domain name but connecting to somebody else's IP address or vice versa? So, like for example, you said you could have multiple IP addresses bound to the same name.
Yes.
And what if I decide to register some arbitrary server of mine under the domain name google.com?
Okay, the question is there any security implication of registering an IP address for an arbitrary domain? Typically, to make an update to a DNS server, you need to be authorized to do it. You can't just advertise yourself as an IP address for some other domain. Okay, the DNS server will not accept it. So, all updates have to be authorized. Okay, so, you can't do what you just said because the mechanism doesn't allow you to change it. Okay, so, just wanted to show you. So, you can, so there are multiple commands you can. So, the simplest one is called host. I don't know if that is visible. Let me make that bigger. It's a little better. So, if you just do host, you will essentially get a reply of this sort. Here you will see that www.csumatch.edu is an alias. Okay, it's an actually, and it will see that it has 2 IP addresses here, right. So, if you probably do it again, it might give you a reply in the other, well, not really. More importantly, not only is this doing this, this is actually using what is called geographic load balancing. This is a content distribution network where the content is the content for this web server is not on one machine, is actually being cached on multiple machines. Okay? And the IP address you are going to get will change depending on where you are doing this lookup. You can actually do this lookup here, and if you go look up that IP address from your home, which may be on, let us say, a different ISP, you may get a different reply. It was always sending you to the closest cache that has the content. Okay? This is called geographic load balancing, where the content is replicated on lots of machines, and then the IP address that you are getting for that service is the closest server. Okay? In this case, you are getting a server that's close to the campus because the campus name server, but if you go elsewhere, you will get a different reply. Okay. But let me show you a few other things. Okay, so here you will see if you try to do this name resolution for CSUMath, you get IP address, but then you get a second MX record saying mail is handled by as a priority level there. Right. So, you can have multiple names. So, if you want to send mail to this domain, it goes to that machine first. Okay, and then, so that essentially gives you the MX record and an A record for this. Okay, and then, and so on and so forth. If you actually, I think, that's not an alias, but let's look up the web server that hosts the course web page. So, you will see that that is actually a CNAME record, where it says that is actually an alias for another machine, that the other machine has this IP address. So, that is a C record, that is an A record, and then there is an MX record. And if you actually give, if you want to see what kind of record it is, you can just ask for verbose responses. You will get a big response saying here is an MX record, here is an A record, these are name servers. So, you will get a big set of responses which tell you all of that information. Okay. So, this is just to show you, you can go and do some of this yourself and try to understand this a little better. Okay, any questions on this before we move on? Yes.
If I have 2 domains and I assign each of them a different IP address and then set one domain as an alias to the other domain, when I then query the DNS server, will it give me both IP addresses or just give me one?
Okay, so what you are asking, if I understood you right, is you have 2 machines, you have 2 IP, 2 A records for that machine, and then you also make one the alias of the other, and then what would happen? So, typically that would be an error, because if you have a C record for a machine, that machine cannot have an A record as well, because either you are an alias for another machine or you actually are a real machine with an IP address. You can't be both saying I have an IP address, I am also an alias for a second machine. That would be an erroneous configuration of the DNS. Okay. Any other questions on this? Okay. So, that is DNS. There are many other things, subtleties to it, but not very important for us. What we will do instead is now with that use case or case study, look for other features we would want in a naming service. Okay. And then to do that, I am going to talk about another naming service called x.500, and we will see that this basically generalizes whatever DNS did. Okay. This is also a distributed naming service. Okay. It is called the x.500 standard. What this mainly does is it allows us to generalize the kinds of lookups we can do. Okay. In DNS, you have to actually only do one kind of lookup, specify a key, you get back a value. Okay. You cannot say list all machines that are within cs.umass.edu and get a list of responses. You can't do that. Okay. If you are doing a database, this should be a database query. You say you write a SQL query with a star and say give me all records that match this criteria, you get a multiple response. That kind of querying is not supported by DNS, but there are many name services where you might actually want to do this. Okay, and x.500 is basically, think of it as a generalization where there is more flexible querying allowed. You can query on star attribute or wildcards. Okay, that gives you multiple replies. Okay. And because you can do this, it can be used for much more than just doing machine lookups. So, for example, you could actually take yellow pages of a phone directory and put it on x.500. Okay. Now, you can say give me all entries that match type plumber, and then it will give you all the entries that match. And you can also do normal phone lookup saying what is the phone number for a user and specify their name. That is a key, you will get a value. So, that is the standard DNS like lookup, or you can say give me all users that have this last name, do not specify the first name, and you will get multiple entries. Right. You can't do any of these kinds of lookups using DNS, but x.500 and their variants allow you to do this more general purpose lookups. So, those name services can be used for a lot more than just mapping machine names to their IP addresses. Okay, yes, question.
How does x.500 do secondary indexing?
Okay, how does it do secondary indexing? So, how it does the lookup, how it does indexing is an implementation specific detail. Okay, typically, what they do when they specify this is they specify interfaces. So, this is the query interface. The implementation is kind of left to the designer. So, you design it. When a query comes in, are you going to have multiple indices? Are you going to do a search? Up to you. You could have asked how does DNS also do, what does it index on, and so on. So, the same problem is that is an implementation not specified in the spec or the standard. Let us put it that way. Okay, so, you can decide how you want to handle it. It is like any database, right. I mean, at this point the naming service is looking more like a database where you can make more complex query. Still a simple database, you can't make arbitrary queries or joins and things like that, but you can do simple lookups on tables. Okay, and then you can construct indices to make the lookup efficient and so on. Okay. Now, I won't say anything more about x.500 because it was too complex, was a commercial failure. But what came out of it is this directory service, which directory service is a synonym for naming service, by the way. Okay, this directory service called LDAP, it's called Lightweight Directory Access Protocol, that is used widely. It's used in most organizations in many under different operating systems. So, essentially think of LDAP as a simplified version of x.500, which does not have some of the complexities. It has the same feature. It allows very general purpose querying and so on, but it removes some of the underlying complexity. For example, LDAP can only run on TCP. Okay. x.500 said it is a database, I do not care what network you use, you can use any network protocol. Okay. So, then things got very complicated because you can use many different scenarios to build it. Here they said okay, TCP IP is the way everybody communicates, let us just say it only uses TCP IP. Right. And then it says we are only going to use one encoding, which is the OSI encoding. Everything has to be encoded using OSI format. You can't say you can do arbitrary types of encoding of databases and so on. So, they simplified some of the stuff. The most of the important stuff from x.500 is still there. Some of the complexities has been removed. Okay. Now, if you know about Active Directory in Windows, that is the Windows Directory Access Protocol, that is an LDAP protocol. Okay. You have something called Open LDAP, which is an open source implementation of it. So if you use LDAP in Linux, you are using Open LDAP. If you use LDAP in Mac OS X, that uses Open LDAP. Right. So there are many operating systems, all of them support LDAP in one form or another. And what these services do is they are basically given you schemas, so you can create users, you can create profiles, and do all kinds of lookups for whether it's their room number, phone number, whether it's their username, and all of these things. Okay. Here's an example of how you might actually take information that is DNS-like and map into an LDAP space. Okay. So essentially, this is just to show you this is also hierarchical. Okay. So the top level attribute is a country attribute in an LDAP naming schema. Then you have a locality, which is the city where is there. Then there's organization, which is the name of the university. The organization unit, which is called an OU record. It says math and computer science. There's a common name, and then there are mail servers, FTP servers, web servers. That's a sample example of how the same kind of hierarchy we saw exists here. But because it's more generic, you start with geography as opposed to using domain names. You start with country and city and things of that sort. Okay. That's the schema you're going to use. Okay. This is essentially the same schema you show in the previous slide, shown in a tree structure where the top level node is a country node and an organization and so on and so forth. Okay. Now, the interesting thing is many organizations use similar stuff. So if you go to the UMass web page and look at People Finder, that's an LDAP service. Okay. So you can actually configure that LDAP service and do LDAP lookups for people's phone numbers, their email addresses, and so on. Okay. So you will essentially see the same kind of records in there, which is there's an OU record and a CN record and so on and so on. You don't need to know details of it, but just to give you some sense of this is also widely used, just as DNS is widely used. But these are used more at an organizational level. It's not like all the LDAP servers in the world are connected together. Okay. All the DNS servers in the world are connected together because there's a global namespace. Okay. Here the naming is hierarchical, but each organization runs its own LDAP server. It does not have to talk to any other LDAP server in other organizations. It might talk to other LDAP servers within that organization, but it doesn't have to communicate with others. That's an important distinction between LDAP and something like DNS. Okay, any questions on this? Okay. So the last thing I have to say, and then maybe I'll continue a little bit on the next topic, is essentially how is naming going to work if nodes are mobile. Okay. We are talking about distributed systems. Okay. Today, most nodes in this in the internet are actually phones. Right. So essentially, your nodes can move from one location to the other. Okay. Because they move from one location to the other, their IP address also changes. Because you might go connect to a Wi-Fi network at one location, your machine has one IP address, and you go somewhere else, connect to another Wi-Fi network, you have a different IP address, and so on and so forth. Right. So that begs the question of how are you going to actually get name resolution if your node is actually going to move from one location to another. So to address this, there was this concept of mobile IP, which is not really widely deployed, but it was actually designed to handle nodes within the IP network that move from one location to the other. Okay. And to implement mobile IP, what you had is every node had a home location. Okay. That was its primary location. Okay. All name resolution was actually based on the home location. Okay. If the node moved somewhere else and its IP address changed, that would be registered with another DNS server, but you would have to notify the home server, so the home server knows where the node is. Okay. So essentially what this says is, because the node keeps moving and I don't know the current location of the node must always register its location with your home location, or the server at the home location. And whenever you try to do a lookup or even try to connect to that machine, you first go to the home, figure out where the node is, then go to that location, do a DNS lookup and connect to it. Okay. So you add one level of indirection to solve your problem. Okay. So that's how essentially mobile IP worked, except that nobody actually uses it, even though it's actually an IP standard. You simply basically deal with IP address changes without having to do something like this. Yes, question?
I'm not really clear about how this is different from just adding another layer in the hierarchy.
Okay. Question is, why is or how is this different from adding another layer in the hierarchy? So the problem is the following. So if you think about, let's say, your laptop or your phone, since it goes from one location to the other, it gets different IP addresses at different points in time. Okay. So if some other entity wanted to connect to your machine, okay, it would need to figure out what its name is and what its IP address is at that point in time. Maybe even the name doesn't change, but the IP address might change. Okay. So how do you handle that scenario is basically the question we are trying to address. Okay. So if you come here, you are going to essentially get some DHCP address, or maybe you connect to eduroam, you are going to get an IP address. You go home, you get a different IP address. Some external entity wants to connect you, what would you do? Okay. Mobile IP is handling that scenario where you assign a home location which is responsible for tracking you at all times and trying to figure out what your IP address is, regardless of what administrative domain you are in. Because you do have to remember that when you change networks, you might change the domain. In one case, you may be on the AT&T network, in the other case, you may be on the UMass network, and so on and so forth. Right? So these are different organizational units, but to make it seamless, you essentially have a home location that's tracking where you are and telling anybody who wants to contact you where to go. That's basically what we have done. We have added indirection into the name lookup service, because although you could, if you knew the new name for the machine, have looked it up directly, you don't know what it is at any given time. So you basically use the home location to track you down. Okay. Any other questions here? Okay. So I won't go much into this, but there is essentially, or the naming problem gets more complicated, especially in scenarios like DNS, if nodes are moving. That's the point you want to keep in mind. When they move, they also move administrative boundaries, and that is where all the problem arises, because you don't know where the node is at any given time. Okay. So with that, I'm going to just give you a quick introduction to clock synchronization today, and then we'll actually continue this after the spring break. Okay. So this is the next topic, but because this was a short lecture, I brought some extra material just to give you some sense of what is coming. Okay. So the next several lectures of the course are going to look at what we call canonical problems in distributed systems. Okay. So these are problems that are going to arise in many different distributed applications. Okay. And we are going to study them in the abstract, so you know how to apply them in various contexts. So we are going to look at things like clock synchronization. How do you synchronize clocks? We are going to look at leader election. If you have a set of nodes, how do they elect a coordinator, which we will call a leader? Okay. If you will look at mutual exclusion, if multiple distributed entities want to implement a lock, how do you implement a distributed lock that spans processes across machines? Okay. That distributed mutual exclusion. How would you do transactions on distributed machines and get transaction type guarantees, which are important from atomicity and other perspectives? Okay. How can you detect deadlocks? Okay. How will you do consensus? There are a whole set of issues that will arise in many different scenarios in distributed systems. We are going to study them one after another, okay, without specific applications in mind, and then later on we'll see how to apply them in specific cases. Okay. So just to give you the first topic, so each of them is a short topic, and we'll take several lectures to cover them. But today we are just going to start with one, which is clock synchronization. Okay. So first problem we want to, not first problem, the first question we want to ask is, what is the problem of clock synchronization and why is it needed? Okay. So if you have a distributed system of machines, you got to first realize that each machine maintains a clock which tells you the time on that machine. Okay. Now the important thing about clocks is that they are not all accurate. Okay. All clocks will have errors, so some clocks will be faster, some clocks will be slower, so they are going to have what is called drift. Okay. If you have actually a wristwatch, which nobody almost wears anymore, or you will know, there's one person wears that anymore, you will know that over time the clock is going to be faster or slower than real time, because the clocks are not all accurate. The same is true of clocks on machines. They are not going to be accurate. So over time they are going to drift. Okay. So now if you are using clocks to timestamp events that are occurring on the machine, and then you want to compare timestamps across machines, if the clocks are not synchronized, then you can't actually reason about the timestamps at all. You can't say, did this happen before something else happened? Because if the clocks are not the same or synchronized, they are drifting from one another or they are actually different from one another. Just looking at the clock values doesn't tell you anything about order of events. Okay. So, because we want to reason about order of events in many different cases in distributed applications or systems, we want the clocks to be synchronized. Okay. And what is shown on this slide is a very simple example of where you might use clocks across machine. And that example is showing you the scenario of what is called make. I presume you all know there are automated build scripts like make and ant and many others that you use to build any software system. The way many of them work is that they actually look at the timestamp of the source code file that you have actually saved on disk and the timestamp of the last compilation of that file. Okay. When was this file compiled last? If the file has changed since it was compiled last, you are going to recompile it. If the file has not changed since you compiled it last, you are not going to recompile it. And since your project may have many files, whenever you run make, it is only going to incrementally compile only the source file that has changed, just to save computational overheads. Okay. Rather than compiling all the files all over again, if you already compiled some of them before, why do it again? Okay. So, you have to look at the file timestamps to figure out which file has changed. Okay. So, there is the file timestamp on the binary file for the .o file for a particular file, and then there is the timestamp on the source file, and you are going to compare. Okay. If you are doing development locally and you are going to basically do your build locally on one machine, that is not a problem, because you are using the clock on that machine. Whenever you hit save in your editor, you are going to create a new copy of the file which will get the current timestamp. And then when you ran make last, you have created some binary output that would have the timestamp of that binary file, and you can compare them and say the file changed since the last compilation, I need to recompile. Okay. Now, the problem arises if your build machines are different from dev machines, which often happens in large organizations. Okay. You basically write code on your local machine, but you have a set of build servers that are powerful, that are going to build a large projects very quickly, because there may be thousands of files to compile. Okay. Now, if you are running make on a different machine from the one where you have saved the file, you are going to have problems. The machines are not synchronized, and that is what is shown here. So, in particular, let us say you just compiled the file, okay, and as you are compiling, you realize you made a mistake. So, you go change maybe one line of the file, hit save, and hit compile again on the build server. If the machines are off in terms of their clock by even a few seconds, what might happen is, but in particular, if the build machine has a clock that is ahead of you, you will see that the timestamp of the file that you just changed and saved is still behind the other one, which you just compiled previously, because that clock is faster. So, the make script is not going to realize that you have actually changed the file, because you made the change very quickly after compiling it previously, and that clock is faster. So, it will not rebuild the file, and you are going to have problems. Okay. This basically says that the two clocks should have been synchronized, and since they were not, you got this. And this problem will occur in many different scenarios. This is just a trivial example of why, if clocks are not synchronized, you have problems. So, somebody had a question. Yes.
Just for clarification, if you have a compiler on one machine and you edit on another machine, it's going to be an overhead because transfer the file from the network. Is that like a universal synchronizer?
Okay. Question is, if you have compiled on one machine and build on another machine, is there an overhead to transfer the file? Okay. Typically, what you assume is the file system is shared. Right. So, the files that you save on your local machine are on some network server, and the same files are accessible on the other machine. So, you are not transferring the files, you are just storing them to a network server, and they are accessible on multiple machines. Okay. So, that is how things would actually work. Okay. So, that is telling you that you need clocks to be synchronized, and then essentially I am going to give you one more slide and then end. And this tells us how you are going to go about synchronizing clocks, and for that you need to understand how clocks work. Okay, so, how do we tell time? Okay. So, essentially in the old days you told time based on basically the position of the sun in the sky. Okay. Noon was defined to be the time where the sun was directly overhead. Okay. That is basically how you said that is noon at that place. Okay. Now, position of the sun no longer accurate, it loses 1 second every year or so. okay, or maybe quarter second. So there are much more accurate clocks, which are the most accurate clocks are atomic clocks that essentially measure oscillations of atoms to figure out how to tell time. So those clocks are very accurate. They'll basically drift by 1 part every 10 to the power 13 second. That is basically 1 second every, I believe, millions of years. Okay. Those are the most accurate clocks that we have. Okay. Now, most typical clocks are not going to be as accurate as an atomic clock. Okay. Typical clock that you might have in your watch or the ones that you have in your computer are basically crystal oscillators. They may be quartz crystal or other crystals, and the way you are going to tell time is use the property of the crystal. Okay. The crystal is going to oscillate a certain number of times every second. So based on how many times it has oscillated, you are going to tick your clock. You are going to say if it oscillates 10,000 times, tick it by 1 second, because it is known that property of the material is it oscillates 10,000 times a second. Right. So you are using these crystal oscillators, but these crystal oscillators are far less accurate. Their frequency might vary based on things like temperature. It's hotter, then they might actually oscillate a little faster, and if it's cooler, they might oscillate a little slower. Okay, so that's going to cause you to be off from real time. So over time, any normal clock is going to deviate from the atomic clock. Okay, so you might actually, so this gives you what is called clock drift. Okay, and then you have to then correct this clock drift by periodically resetting the clock. Just as if you had a wristwatch, you are going to say, I'm going to change the time on that clock. Okay, same is true of any other machine. You just use an automated program to do this. Every so often, you go to an authoritative time source, ask for the clock value, and reset your clock. Okay. So the standard thing is you will basically go to an atomic clock somewhere that you have access to, look at the time, and set your time. Okay. Now, you don't actually go to an atomic clock. There are many other services that will actually transmit the atomic clock value to you. So you go to one of these services that will tell you what it is and will set the clock. Okay. Most cell towers will actually transmit the clock value because they are themselves synchronized to an atomic clock. So your phone, for example, will automatically synchronize itself. So it's the clock on your phone is actually accurate because it is periodically synchronizing itself with the cell tower. That's why it doesn't drift. Okay. The one on your computer, unless you actually have a time synchronization protocol, will not synchronize. It will drift over time. Okay. So you got to implement a synchronization protocol to ensure that your clock on the machine is also going to not drift too much from any real time. So at the essence of all clock synchronization protocols is the need to synchronize an actual clock which is no longer accurate periodically with some authoritative source. Okay. And the way you do this is going to give us a sequence of different clock synchronization algorithms. Okay. So we won't start talking about them today. This was just a primer on why we need clock synchronization. What are clocks? Because they're not accurate, you need to synchronize them with something authoritative. And here we are going to use our atomic clocks to use as the authoritative source and then synchronize with them. Okay. So next time, which is actually after spring break when we meet, we are going to go into specific clock synchronization algorithms. Okay. So today we are going to stop here. Okay. Just an announcement, since there is a lab due, I'm going to see if the TS can be available to you either physically or electronically for the rest of the evening. Okay. So that if you have any last minute questions, they get answered on time before the deadline. Okay. So let's stop here. Have a good break. We'll see you in a week and a half.
Can I do a last-minute team merger with my friends?
Oh, yeah, sure.